Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to introduce Akanksha Chaudhary, a PhD student from Stanford, who's interviewing for a postdoc position here at MSR. Akanksha works in an interesting space on DSL and just fiber at the low layer of the network stack. She was an intern with us last year, and she did some work on dynamic spectrum access. That work was very valuable to some of the responses to the FCC's NPRM we filed from Microsoft. Akanksha has also won numerous awards. She was a silver medalist from IIT Delhi in the EE department. That means she was the person with the highest GPA. She's the first woman to win the Marconi Young Scholar Award, right? That's a prestigious award. So she's won some great awards, and today she'll tell us about some of the exciting work she's been doing as part of her thesis.
Thank you, Ranveer, for the kind introduction. It's always great to come back here, even though it's rainy weather, you know. So I'm very excited to talk about my research and tell you all about how we can squeeze multi-hundred megabits per second to gigabits per second out of copper, which is really economical. And this work is in collaboration with my advisor, John Chaffee at Stanford, and my colleagues, Hao and Halima. Hao has already graduated. So let me begin with a big picture overview. What we see in this picture is a home network. But instead of having a single PC connected to internet, what we see is a numerous set of devices ranging from your Surface, Xbox, phones, laptops, to here we have IPTV. There are three trends that are apparent in this space. What is apparent is that there's an explosion in terms of the number of connected devices. In fact, we expect by 2020 there will be 50 billion connected devices as per Cisco projections, which are rather conservative. But what that means is that's 5 times the population of the world. So on an average, you would have roughly 5 to 10 connected devices per home. So that's a lot of devices to support on each home.
But the 50 billion number is not for home devices, right?
It's for outside, yeah.
So these are mostly cows wearing sensors.
Yes. Cows wearing sensors, okay. That's a nice analogy. What's more interesting in this space is that these connected devices are not connecting only via cellular connection, as you just mentioned. They are increasingly offloading to the Wi-Fi or the femtocell or the small cell inside the home because the spectrum is shared and you no longer can support all of it on your cellular spectrum. So increasingly, the topology or the architecture we see is you have a Wi-Fi modem or a femtocell modem or some kind of small cell, and then a wired connection to get to this modem, which provides the internet access. And then thirdly, there is an increasing demand for streaming video. And by streaming video, I mean it's explosion in terms of IPTV subscribers. There's YouTube videos increasingly being watched, and a lot of video streaming or video conferencing is happening in this space. So to summarize, we do not have enough spectrum in wireless, which is why I was working with Ranveer last summer. And it's shared medium. So to support these devices inside the home, we want to be able to get this wired connection somehow at high speed. And this is what my talk is going to focus about. How do we get this wired connection, which used to be in the range of 1 to 10 megabits per second, to multi-hundred to gigabits per second to support all these devices? So to give you a big picture overview of what I mean by this wired connection, what are the options? So this picture actually shows you the number of subscribers and how they're growing in worldwide wireline broadband access market. You have 3 options. You have fiber, and in news you increasingly hear Google's fiber. You have cable, where cable you usually hear Comcast doing that, and then DSL you increasingly hear AT&T working in this space. What I want you to take away from this graph is that, so worldwide DSL is the largest fraction. It's 67% of the fraction total. And more interestingly, And the second largest is cable. And the reason this is increasing is because in developing countries, the penetration is increasing. But very interestingly, even when you are increasing the fiber connections, you are not running it all the way to your home. In fact, you're running all the way to your curb or your building, and then you're using the existing telephone cable or the TV, that's the cable connections, to provide access. And why is that the case? Economics drives it. So it's simply economical per subscriber to do cable or DSL than to do fiber. And the joke there goes, sorry, go ahead.
Economics drives it. What you mean is there is copper everywhere already.
Exactly. Laying down fiber all the way to your watch costs additional money, while historically DSL was the telephone line connections that were laid 100 years ago, and then cable started out as TV that was laid, again, decades ago. So now that we know what our options are in wireline broadband access, where do we go from here? What kind of speeds can we support on that?
It's getting expensive. So do you know about the difference in prices, like per meter, between copper and fiber? I'm just thinking, like, for new deployments, like new neighborhoods coming up, what is, like, are we still going to be like lining up copper, or are we going to put in fiber?
Actually, that's a great question, and the answer lies that metal, as a copper, is a valuable metal. So actually, the price, the glass might be cheaper. It's deploying fiber, as in building the network, is where the value or the cost goes up. Per meter, I think copper will be costlier. The fiber is roughly the same cost. The new deployments, I would maybe prefer.
That's an interesting style, which is like in developing countries where labor is cheap, extracting copper and replacing it with fiber actually is a net gain, because you can extract the copper and sell it, and fiber is very cheap, and labor is cheap to make that switch.
Okay. No, but what you are roughly getting at is, at the end of the day, someone has to pay. And why would you pay for gigabits per second if you're only going to use 100 megabits per second? So that's where the value ends up being. So the topology that has been supported is run fiber all the way up to, say, MSR building, and then run copper all the way up to your homes, because that's an existing infrastructure. And all of you don't want to pay $100 per month to get 100 gigabits per second to your office. Maybe? Okay, Victor, your bill is going up.
Well, no, I think I'm paying too much.
I think the story is that there's already, there's countries where you have already the Cooper line laid.
Yeah.
And I believe that's the majority of the 400 million you see.
Anyway, this is sort of moot point. This is the statistics you're providing. That's okay.
Okay, so let's actually do some technical work here. So we were talking about 10 megabits per second is what an average customer gets today, maybe 5. With viewers, you can actually go up to 40, 50 megabits per second. But I'm talking 100 megabits per second or gigabits per second. Why is that not possible today, and how can we get there? So what this picture is showing, so this is your home network where you will have a modem. This is a copper line which will run all the way to a DSL access node, and this DSL access node was deployed by a service provider. And this is connected to the core network. Increasingly, this DSL access node might be at your curb or close to your home, and a fiber might be deployed between service providers, central office, and the access node. Sorry, wrong way. What's interesting here is that these copper lines are shared in the same, they share the same cable or binders. So what this picture is showing is that this is the wire that's laid inside the network, and these wires are shared inside that same cable. Why is that interesting? It's interesting because it introduces noises and interference that bring down the speed. So there are two major problems that hamper the performance in DSL networks. One is intermittent noises, and these noises come from in-home devices. So this is the noise injected at the home end. The other is from copper impairments. You often have bridge taps or other kind of impairments which already exist because these networks were laid down much earlier, and you don't necessarily know what exists out there. And then this is radio interference from AM radio or other radio bands that exist in the same spectrum, which is really 0 to 1 megahertz, or it's roughly 32 kilohertz to 8 megahertz. And this is the problem that I was talking about, where multiple copper lines share the same binder. So this will be a binder, and when they share the same binder, they'll crosstalk into each other, and crosstalk is similar to your interference in wireless. And imagine two antennas placed right next to each other and then leaking signals into each other. That's the kind of interference we're talking about. So how can we handle this interference? Can we do something smart about it? So traditionally, the service providers only configured this network. So they built this modem, they had this line, they will provide you the modem, you connect to it, and you get the speed. So they had designed the modem for worst case scenario. But now we can actually manage it in the cloud, and that's what I'm going to talk about. And this is where my work comes in and my advisor's work comes in. I'm going to emphasize what my contributions are in this space. So that's what I call the dynamic spectrum management approach. So dynamic spectrum management is really a more broader term than just managing the spectrum. And I'm going to start with an overview of what I mean by dynamic spectrum management in the first part of the talk. Then I'm going to focus on a specific problem that exists in next generation DSLs called vector DSL technology, which is an exciting space, an upcoming space. And then I'm going to talk about certain extension to cable access networks that we are working on right now, and then other research projects I've worked on. So this is going to be how I'm going to structure my talk. So let's start with dynamic spectrum management. So this was the network that you're already familiar with. We're going to use a spectrum management center. The spectrum management center is simply some device in the cloud which is collecting data from the core network about what kind of performance is happening here. So imagine you have a server somewhere which is collecting all this data. This is very similar to software-defined networks, for those of you who are familiar with those. And what is really happening is that on a data plane, you're collecting the channel and noise conditions via something called as SNMP interface. And the kind of things you collect are channel or noise values, data rates, retrains, error rates, as a few examples. And then what you want to configure is you want to somehow reprofile these lines, or basically configure the lines so that as a service provider, you can make more revenue and give better network performance to your subscribers. And the kind of things you will change, and I'm going to talk about this in details, is power, codes, margins, speeds, and then use some kind of sophisticated signal processing in the next generation technology. So the point that I want you to take away here is that these are really software-defined access networks, if I may use the term. So instead of software-defined networks, we are really using access networks and then somehow configuring them in software instead of using the worst-case design where the modem was pre-configured for a worst-case scenario. And being able to use all this data and change the algorithms on the fly and make the entire network adaptive is where this gets really interesting. So what can we do in the control plane? So let's go back to the fundamentals, which is channel capacity formulation, where this is what we can get out of our channel. This is the capacity that we can get. This is the bandwidth. And then the capacity is logarithmically proportional to the signal and noise ratio. So what we can change is, one, we can change the coding. So we can change the power levels. We can change the receiver structures and how we detect, whether we detect symbol by symbol or sequences. That's the physical layer aspect. We can change the number of dimensions. And this is another interesting space. We can increase the bandwidth over which we are receiving the signal. We can use more antennas. So if I start detecting multiple copper lines at the same time, instead of detecting a single line, I'm using spatial dimensions, just like using multiple antennas in wireless space. And then this is the noise aspect, and this is whatever we can't cancel. So in the control plane, we are somehow trying to configure these values, change this by using signal processing, and this noise, I'm going to basically get rid of it when I can. So in the single user, what I'm showing here is this channel actually varies with frequency. So usually we are used to single carrier systems where the channel is pretty flat. In this case, the channel attenuates with frequency. So what this is showing, the bottom curve, bottom black curve is showing is noise over channel gain, or if you may think of it as inverse over channel gain. The optimum thing to do if you have a bandwidth of W here is to water fill. And just to remind you what water filling means is that when your channel is better, 1 over channel is worst, you want to fill more energy. And when your channel is worst, or 1 over channel gain is better, you want to fill less energy. And the best distribution of how you should load energy or power in this space is up to a single water level. So that's the water filling solution, and this was proposed much earlier. The way you can view this is that you're basically chopping up your entire spectrum into small into small chunks, and on each you're using optimal energy to get the capacity, and you're basically adding them together. So that's the same channel capacity formulation.
So just a quick question, clarification. So at what time scales are you thinking of adapting the system here? Per packet, or a few seconds, minutes?
We are going to change on the scale of hours. We are configuring the network. This is not wireless.
Okay.
Yeah.
And this
So this
fading noise curve.
no so okay, so let me clarify your question. So as a network service provider, I'm going to configure at the level of hours. As a modem, I'm going to adapt at the level of minutes. So 30 seconds is the training period for a DSL modem. So what ends up happening is that if I see a very large noise, then I do not want to adapt to it. If I do not adapt to it, I'll have to retrain. And by retrain, I mean I break the connection and then I restart the connection. So I would be basically doing it at that level. I basically do not want to retrain if I can maintain the connection. Because retraining means that if you're watching a football match, the football match will freeze right there, the connection will break, and then it will restart. Okay? So to clarify your question, I'm going to, let me get to the point that I'm going to make out of this slide. So the reason I was talking about these multi-carrier systems is that each modem can use this multi-carrier transmission or this adaptive bit loading to adapt to the noise that it sees here. So that's the first aspect. We had multiple cross-talking users. What gets interesting here is that for a single user, you were simply water filling on noise over channel gain. When you add a second user, your noise now depends on the interference that you see from the second user. So as a result, you need to fill power on top of this interference now. What we have found in this, and this is the solution that we proposed, was something called as multi-level water filling, where basically you end up decomposing the entire spectrum into multiple bands, where in each band you're doing water filling. And the users emphasize one band over another based on whether that's good or bad for the network. So that basically ends up happening. And I'm going to explain this in much more detail. This is just an overview. So to collect the 2 points that I made.
Can you clarify, are all users using the entire frequency band, or you are also going to separate them out?
That's a great question. So when you say multi-carrier with adaptive bit loading, I can choose how much power to put on each tone or each chunk. So I can say that I want to use the entire band, but I can put power differently on each tone.
And the modem does that?
Yes, and this is the configuration technique that it's using, which is called water filling. So I want to somehow tell the modem what kind of water filling to use, how much power to use to configure this technique. And actually, when I showed this water filling, this is actually the simplest thing that they can do. And for those of you familiar with the area, it's called Levin-Campello. It's a greedy scheme to do bit loading, and it's already implemented in modems today.
So when you talked about retraining, is training the process of setting these power levels, or is it?
Yes.
Okay.
Yes, but you can change powers on the fly. You can change bits on the fly using something called as bit swapping. So training is basically when I'm doing the training sequence to detect when the channel and the noise is set up.
So when you say OFDM is each subcarrier, you have a different power level? Is that how it is done?
Yes, exactly. So the reason I used OFDM with adaptive bit loading is because in wireless systems, OFDM is equal bit loading, at least traditionally. But here on each, I can choose the number of bits, and they can go all the way from 2 to 15 bits. That's how it's configured. in these systems.
This is jumping ahead though, but let me ask.
Yeah.
So why is this not?
Let me complete this slide and then you'll
I was
have.
going to ask this last comment.
Okay, go ahead.
The last comment was on the adaptive bit loading. Why don't we see more of this in the wireless domain?
Why don't we see more of this in the? Because the most gains that you get out of wireless are really in the coding space. So if you use 2 bits versus 6 bits, you're not going to get as much gain as you get out of putting a strong code on multiple tones. So they can do this, and there are some gains, but because the fading happens, the variation happens at such time scales that putting strong codes or putting a lot of redundancy is where you get the most gains in wireless systems. Does that help?
Yeah, it does. I was just giving me a sense of what your fading models are.
Okay. No, so really when you talk about, this is not really fading systems. When I talk about problems here, this is in-home interference or radio interference, which crops up once in a while. So we talk about outage probabilities, but we are really trying to not get the modem to retrain too often and the subscriber to complain.
So how wide is each?
It's 4.25 kilohertz. Yeah, so we are talking about, so in the largest, the VDSL, which goes all the way up till 17 megahertz, you can have all the way up to 4,096 subcarriers. And in ADSL1 today, you can have, ADSL1 had 128 and ADSL2 Plus had 256 subcarriers. So we really have very large values of N here. So I don't want to run some complex optimization scheme, which I'll get to. So this is a slide which I really like. So let me take a moment here. So this is the network which you already had. And this was connected to the core network. I already introduced you to the Spectrum Management Center, which is collecting the data and is going to control it. At level 1, I can choose the codes. So I can control each line on a line-by-line basis. So I have the data for a single line, and I can choose how to provision the coding scheme on that line, how to provision the rates on this line so that I can get rid of these copper impairments, this in-home interference, and this radio interference. And how I'm going to do that, in short, will be somehow use a coding scheme and a provisioning scheme that will make the line stable. So don't run it faster than it can support. And why is that a challenge? That's a challenge because when you did not have noise statistics, you had no idea what the line was doing. So you were just shooting your arrow in the dark. And
this is happening at what level? Like, this is happening, how many homes are you thinking of? How many devices?
Millions.
And this is happening all in the SMC?
Yes.
Okay.
So the algorithms that the algorithms that I am proposing are more generic and generalized. In terms of actual implementation, this is happening at my advisor startup, so they are actually working with millions of lines.
Wait. So do you ever do decisions across these labs?
Yes.
Oh, so what do you do across these labs? Is there an optimization to be done across different these labs, or this is just these lab level optimization?
So it depends on how much information you can share. Can we do that later? Because I'll not get to the slide. I'll do that at the end of the slide, I promise.
Okay, binary answer.
Yes, you can do it.
Okay.
You have to get permissions of data you can share.
I see. But technically, there's value to actually optimizing across these labs.
This is a binary.
Okay, let me get through the slide and I'll get to it. No, that's great. I like questions. That's great. So DSM level 2 is really the idea of what I was explaining in that multi-level water filling. We are basically configuring the energy on multiple lines to get rid of this crosstalk. Now, can I get rid of this crosstalk? Not really. What I can do is I can manage the crosstalk. I can say that I'm going to load less power in certain bands and hence introduce less interference into others. And then vectoring is where we actually cancel the crosstalk and noise using signal processing. And there's another technique called bonding, which you'll see in news, which is basically creating more bandwidth by putting multiple lines together. So what you need to remember out of this slide is that now, with these three increasing levels of complexity, you can actually get a lot more bandwidth out of these systems. And in the next slide, I'm going to show how much more. But just to give the takeaway points, we are really shooting for higher speeds Improved stability, because stability means that you will not call AT&T to say, hey, my DSL line is not working. Longer loops, if I'm a service provider, I want to provide the same rate for a longer length of loops, and then reduced costs, because I don't want to invest or upgrade my networks if I can choose to do that. So here, this is a graph which summarizes roughly the kind of rates you can get. So let's look at what this is showing. This is the DSL loop length from customer premise, so this is your home, up to the deployment boundary, which can be up to access node, which is at the service provider. And these are the data rates. So notice they are going from 0 to 150 megabits per second. I haven't plotted the gigabits per second, which are possible with DSM level 3 plus bonding. So let's focus on how we get towards this direction. So anytime I'm deploying fiber to the curb, I'm going to basically move on the curve here, so I'm going to increase the data rates. Very simple principle, you're reducing the distance, you're bringing down attenuation. This is the space where we are working. This is when we are using the data. So from no DSM, which is the blue curve, at 500 meters, when I go to DSM level 1 or 2, I started at 40 megabits per second. I've gone all the way up to 55 to 60 megabits per second. That's 37.5% gain. And with DSM level 3, we've gone all the way up to 125 megabits per second, and that's really 200% gain. So this is really the interesting space which most telcos are entering now. Now I can get to your question. We can answer either way.
What is the phantom bonding you basically mentioned on this slide?
Bonding, I'm not going to talk about. Basically, you club multiple DSL lines together and use a passive optical network kind of architecture.
Multiple DSL lines together and still basically sending information to each client?
Yeah. I can talk about it. Let me get to this question.
Is this a simulation result or this is the real number on the DSL line?
So that's a great question. This is real. This is starting to get deployed, so DSM level 1. So I mean, these results are from simulations, but this is already getting commercialized, and vectoring is something that has been demonstrated in labs. So that's.
Which curve is simulation? Which curve is real?
They're all simulations.
They're all simulations, but I'm just telling you that what has been commercialized and what's not been commercialized. So we're getting here. We are going to get here, but this is the stuff that we are in right now. And vectoring, they are starting to move, and I'm going to show you what the space looks like. Your question.
My question was like just around like what. So you talk about a bunch of like interference and impairments. I was just wondering, when you do optimizations across DSLAMs, what is the value of that? Like what
So
exactly do you
the
gain?
key value that I want to get as a service provider, let's say I am AT&T and you are another service provider and we are competing, we want to get the maximum value out of our networks. So we want to basically provision maximum number of subscribers at whatever rates they're paying for, right? How do you do that? You basically want to bring down the interference that these guys are creating to me and I want to creating to them. So that's where the key value lies. Other than that, if there are impairments, I want to somehow tell these users to not blast power, because the coupling between multiple lines happens really at the power level. If I'm going to blast power on my line, it's the cocktail party problem.
Two different DSLAMs, they interfere or?
No, so, oh, okay, so that, I confused your question. So in a single DSLAM,
Right.
so at any time, the lines that will interfere are the ones which are in the same cable. They can terminate at different DSLAMs belonging to different service providers. Because DSLAM is owned by a service provider. It is the box that I carry. I'm AT&T.
Well, I was just getting, I think riffing off of Victor's question, when like the optimizations are happening purely at a DSLAM level, or you're actually there's some optimization that's happening. Like, do you take like, while configuring a DSLAM, do you take other DSLAMs into account or not?
I can, statistically I can. What I'm getting is that if I want to do that as a spectrum management center, I need permissions from both in commercial deployment.
Did I hear you right? Did you say that different wires can go to different DSLAM
Yes.
numbers? And that's
Yes.
why you need to, so basically,
If there
Everybody
is
has different
unbundling.
pieces of information in some sense, right? I have like information of this.
No, that is not very common because in US you don't have unbundling, but in UK you have unbundling. So in a single cable, I can lease lines to multiple service providers, and then each one can take their box and say, this is what I'm doing with it, and we can actually, you'll see some of it. So yes, every line can have different pieces of information, and that's where the big fights happen in standards where, hey, this is guy is going to blast its power, why should I not be allowed to blast power? Okay. So any other questions at this point? Because this was my overview of DSM, and I'm going to now emphasize one particular problem. No? Okay. So I'm going to...
Question about the phantom bonding.
I can answer further.
He was asking about
I was asking what is the phantom bonding?
So what is happening in phantom bonding is you basically take multiple lines and you're delivering data to your users, right?
Okay.
So you somehow want to use these two lines together to deliver data in time. So you basically use a different architecture.
So my understanding is, for example, this level 3 is like interference alignment.
Yes,
So
yes,
basically, I mean, basically able to cancel out the interference.
Exactly.
I'm just trying to understand.
So bonding is really happening at higher layer, where basically you're putting packets together from multiple things. So it's like, I think the simplest way to explain that is, okay, just imagine that I have two Wi-Fi modems, you and your neighbor, and they decide to cooperate. Then I'm going to send packets to both the Wi-Fi modems, and then I can stream the packets to you. So they're basically happening at packet level.
I mean, you need the two modems to communicate between them
So
to basically allow the bonding to happen, right?
Yes. You need some way to somehow, yes.
So you need to basically assume there's a back channel for them.
Exactly. But this is starting to happen.
Oh, really?
Yeah. There are startups looking at it. Basically, they're putting packet by packet information together because there are a lot of open Wi-Fi. So they're trying to look at that. Again, what is not clear is how much value you can get out of it in real systems where Wi-Fis are not open yet. So that's a space which people are starting to enter, and the gains have been demonstrated in simulations. Any other questions at this point? Okay. So at DSM level 1, basically my work has been on developing a tiered rate adaptation approach and showing using noise statistics to improve stability. And what in terms of impact, I really took it to UK NIC standards. That's the telecommunication body there, and it's now commercialized. So I actually participated in the standardization process and talked to a lot of companies in that space. At DSM level 2, we proposed, so there existed optimization algorithms for those of you familiar with the space. We came up with a practical approximation called as multi-level water filling that is robust to changes that happen in noise levels. So coming back to Jeetu's questions, when noises change at levels of seconds, now actually you can bit swap instead of imposing certain conditions. I'm confused. I'm really sorry.
He also gets confused between him and
Okay.
Sometimes I wish I were Jeetu.
I'm really sorry.
He's actually watching.
Darkest moments, yes.
He's actually very sick, but he's watching this office.
Okay. So here I led the standardization and in US ATIS, which is American Telecommunication Standards, called COSNI group, and then UK NIC group. And then DSM level 3, for practical deployments of vectoring, we proposed novel DSM algorithms, and here the theoretical bounds were also not understood, so that was also something we have derived. So this is where we are going to spend the rest of the talk, barring the last part. So this is the exciting part next. So what is the difference between legacy systems and vectored DSLs? So looking back, this is a cartoon of modem to DSLAM. Port 1, this is the line card, and this is modem 2 to port 2. What we were doing in earlier DSLAMs was that I was decoding the signal at a single user level. So in an information theoretic sense, this is interference channel. And the speeds I was getting was between 1 to 25 megabits per second, of course, depending on the length of the line. With vectored DSLs, I'm really using a common receiver. So instead of decoding signal at each port, I now have some mechanism to decode signals together. So you're using sophisticated signal processing. In the information theoretic sense, this is really looking like a multiple access channel, and you can start with speeds of multi-hundred megabits per second. And in wireless domains, this is really like putting two antennas together, and then at the upstream direction, you are decoding both the signals together.
Is the performance improvement you're talking about here only for the uplink?
No, this also for the downlink. I'm going to focus on upstream because that's where I have most of my simulation results.
Okay.
But downlink, it also works, and there are very interesting results there too.
It's obviously a different approach, right? Because you can't.
You can do pre-coding.
Okay.
Yes.
Okay.
So you're not decoding, but you're pre-coding. There are certain limitations to that, but we can talk about it. So this is a nice slide that I wanted to show as to why is vectoring exciting? Why are we excited about it now? So notice that the dates here are all late 2012. So a lot of telcos at this point are starting to move towards vectoring because they see that out of legacy networks, they can squeeze a lot of speed now. So AT&T has announced a $14 billion investment into Project VIP, which was in November, and they're moving it into different cities. And you hear Google Fiber all the time, but AT&T is getting into this space big time and trying to get the maximum out of their networks. Deutsche Telekom, which is in Europe, has committed to the fiber to the curb and vectoring, and they are increasingly upgrading their lines. Something like 25 million lines are being upgraded. And then Huawei, which is really the DSLAM manufacturer, is also spending a lot of energy into moving towards vectoring. So just to give you an idea, I've just picked some news pieces to say that at this point in time, a lot of companies are excited and putting a lot of money into this space to actually see how much they can get in real networks. Okay, so what are the problems they would face when they go and actually deploy this in real networks? And this is where things get really interesting. So here, this was my DSLAM. This is my earlier DSLAM. Here I was doing single user by user decoding. And here I have upgraded my lines, and I basically put a common receiver to decode signals. When I'm deploying, can I upgrade 50 to 200 lines in one go? That never really happens. AT&T doesn't decide that I'm going to upgrade 200 lines at 2 a.m. at night. That never happens. So incremental upgrade of subscribers, just to make this deployment possible, it's important that I should be able to incrementally upgrade the number of lines that are vectored. In unbundling, you will often share lines between legacy and this next generation because different service providers move to different technologies at different points in time. And in UK, you have these different service providers which lease lines out of the same binder. And then the most important point is that in terms of a service provider, I will only upgrade my lines if I have the economic incentive. So if I have a cable or a binder which consists of multiple lines, the maximum gains I get are when the lines are really short. So those are the lines which I'm going to upgrade. So you might be limited in signal processing or economic incentive. So when you need to get that, when I go and deploy vector DSLs, they'll often exist with the legacy DSLs. I want to get maximum value out of what I'm upgrading, at the same time keeping the customers that I already have happy. And why is that a challenge? So the data rate gains can be very limited if I use the existing state-of-the-art solutions based on what I already know. So we understand interference channel. We know how to handle this. We know how to handle, for example, multiple access channel in information theory. And when I maximize the data rates of these two systems independently, because I just upgraded my DSLAM here, but I have no way to know what I should do to configure powers here, I'm going to have this crosstalk that is happening from these vectored systems into non-vectored systems and non-vector systems into vectored systems. And both of them can take away the gains that I get out of my vectoring technology, the new technology that I just upgraded. I'm going to call this mixed binder iterative water filling, and we can go into details later, but the intuition here is based on the multi-level water filling solution that I was already doing. They are only aware of the interference that they see, and these people have no idea what is going in the rest of the network. They're just canceling interference that they're seeing. So it's the inter-domain interference which becomes the challenge. Can we come up with solutions which are practical enough to take that into account?
Is this problem temporary? Till like
no.
All those, it's not temporary.
It's not temporary. In fact, one of the very interesting papers that recently came out from telcos was that often you only want to upgrade parts of your system. So you want to put a DSLAM and then another DSLAM with limited signal processing, so tiers of your system. So they basically want to do partial vectoring, is what I'm getting at. So it looks temporary because I'm talking about incremental upgrade, but often they want to do partial vectoring because these are business decisions which are made by companies. So if I have 50 million subscribers and 5,200 lines, I only vector, 10 lines, if that's where the most value lies. Because vectoring subscribers are also supposed to pay more. If I'm going to get 100 megabits per second, I'm going to pay more for it as opposed to 10 megabits per second. So I'm only going to upgrade what I have the economic incentive for. Any other questions? So this is a flavor of what exists out there today and why that's a problem. And I'm using a very simple example. So here we have two lines which are vectored and one line which is non-vectored. These two lines are using, these are 300 meters long, and this is 1,200 meters long, and this is showing the crosstalk that is happening between the two users. What this plot is going to show you is the data rate that we are getting on these vectored lines, which are of the order of hundreds of megabits per second, and the data rate that we are getting on non-vectored lines, which are of the order of 6 megabits or 10 megabits per second. So what we observe here is that as we upgrade this line to hundreds of megabits per second, on the legacy line we have lost the data rate. It's 1/3 of what existed out there, which I'm sure if your neighbor upgraded, you'll not be happy with. And then, so, or the other way to look at it is that if I wanted to upgrade my technology and maintain 6 megabits per second here, then I'm not really getting any gains out of the new technology. So that's not fun as a service provider. And the real problem here is that you're not able to reduce the crosstalk in the mixed binder scenarios. Now that's an easy thing to say, but we don't even know the theoretically optimum solutions in this space. So,
can I ask you a
sure.
high-level question?
Yes.
Why should we believe your simulations?
Why should we believe my simulations?
Yeah, because we here build
prototypes and
you've been with
such.
us, right? So you
Yes.
kind of know how we work. And so you're presenting to us a lot of results with a lot of simulation, and I'm actually very appreciative, and I think that's great. But why does the industry? I mean, I also sort of understand the scale maybe is not possible to actually implement. But how do you go about convincing folks that invest in this technology because what I've done is actually totally accurate? Can you give us some background of what sort of simulations you're doing and what tools you're using and why?
So the tools that we're using are actual channel data. So often we take the data from actual channels or the models of the channels, and then we are simulating based on the techniques that we are seeing at the transmitter and receiver signal processing side. So in that sense, they're completely believable, but of course in real environments you see a lot more impairments. And to counter that question, I mean, of course no one will invest in this. So I don't want to say this on video, but the point is that this is actually being deployed on the other side of the network. Yeah, it is being tried out. So we are developing the theoretical tools on Stanford end, and then this is being tried out on the other end.
You talk about basically getting channel data and use it for simulation.
Exactly.
Then an important question like Ratu asked is the timeline.
Okay.
Because you have different interference signals, right? I mean, for example, household appliance, radio, I mean.
Okay, so at this point we're dealing
timeline, right?
Yes. So the best way to answer that question is the reason why we have these 3 different levels of DSM. So the first level of DSM is really handling this interference by talking about what kind of things go up and down. The crosstalk is a persistent problem. So here you're trying to cancel it. So the timeline issue is really handled to maintain stability.
Yeah.
And then the crosstalk issue is really to get rid of the interference.
Here is this, for the crosstalk channels.
Yes.
I mean, in reality, how stable that crosstalk channel is. So for example, in wireless interference alignment, right? I mean, basically you need to measure this.
Okay, I can answer that question very simply. How often do you turn on your DSL modem or turn it off?
If it's turned on, and I mean, basically if it stays on, is the crosstalk matrix relatively stable? Because, I mean,
Yes.
potentially can have other things. For example, the wind blows. I mean,
Yes, of course.
basically, I mean,
It's not just on, it's also how much when you're using it to deliver traffic, right? So it's
That's exactly the question where that should be the next level of DSM, where they should actually turn it off when it's not being used. That's being looked at.
It's always interfering? Is that how it works today?
Yes.
Okay, wow.
Sends empty so that you can.
That sucks. Okay.
Yeah, it's unlike wireless. That's a great question. That's where people always get to me. It's like, yeah, they should turn it off. I mean, there is a low power mode, but no companies out there actually use it so far. They're trying to get there because energy consumption is becoming important. So that's really the next dimension. But right now we're talking speeds and not energy. That's like, okay, let's.
It's a problem. Your crosstalk doesn't rate even a per
Yeah, which is
No, but the vectoring, all the things that I'm saying, these are adaptive receivers. So they're basically going to run with an adaptive loop, which is your LMS filter, and they're just going to adapt to that matrix. Now, if things change at the scale of wireless, the gains will start going away. But as long as they don't change at that level, you are still in good shape. Now, why should we believe it? So, I mean, there was a demo that the startup that I'm talking about actually showed that this is working stuff now. So my job was to take it to standards. It was like convince people that this is a viable solution.
And apparently they're convinced, and so they're putting stuff in.
Yes.
So the stuff that's in the standards is your stuff. Is that right?
Yes. Yes, Stanford.
Directly with you, yeah.
Yes.
Well, you and Stanford, yeah.
Yeah.
That's great.
Okay. So, and the key idea we are using in all these is basically not to load more power than is necessary at any given time. So we are at 40 minutes right now, and I wanted to cover two approaches. One was the optimization-based framework, where we are actually developing theoretical solutions, and then the heuristics-based approach as to why the practical approximations make sense. So I want to get some sense of time as to 20 minutes? Okay. Okay, so in the optimization-based framework, I'm just going to give you a heuristic perspective and not go into every single detail. But I think most of you will get because I showed pictures earlier. So we already talked about this is an adaptive bit loading system. So there is power on each tone. Then there is a data rate associated with each vectored user. And there's a data rate associated with each non-vectored user. So one of the simplest formulations of modeling the problem is to come up with a weighted sum rate maximization, which Jin would be very familiar with. But what we are really doing is we are trading off the rate that we can successfully decode at non-vectored lines versus vectored lines. So there is a trade-off. As I increase the rate of the vectored lines, I am going to not be able to decode more at rate for non-vectored lines. So there's this boundary, which we call the achievable rate region, which we can get by using a weighted sum rate maximization formulation. And how do we move on different points in this boundary? We're going to put different weight vector for the rates that go to non-vectored lines and the vectored lines. So this is the mathematical formulation, and let me parse this for you. What we are really doing is we are maximizing the sum, the weighted sum of rates of vectored lines. So this is the rate of vectored lines, and the weighted sum of non-vectored lines with respect to two constraints, and very simple constraints. One is coming from total power on all tones, so my modem cannot transmit more than a certain amount of power. And this is a PSD mask constraint, which is basically saying that on every tone, FCC limits how much power I can put. So what can I get out of these? So my optimization variable here will be power. Now, why am I interested in this problem, and what am I really doing? So what we understood was this part of the problem was understood alone. This part of the problem was understood alone. Putting the optimization of these two together and then coming up with practical approximation is really where things get interesting.
Question.
So, yes?
For these formulations, I notice you are maximize the total weighted basically value of the rate.
You can use
we
other
talk about the rate utility, yes.
We can talk about rate utility, but here
Radio utility means the
I know.
utilization, the utility value of the rate may not be linear.
Exactly.
Right? I mean, 1 megabit versus 10 megabits.
Exactly.
It's not 10 times.
Yeah, you can talk about rate utility, but I just chose to show the simple formulation. You can easily put a function of rate up there. But as you know that when you put utility, then water filling is no longer the optimal solution anymore. Right?
I think in reality, a rate utility probably makes more sense.
No, what ends up happening is that this weights. So when you put, for example, log utilities even in wireless systems, it ends up being this weighted utility in the smaller time scales because you just change the weights. That's all that is happening. You basically have 1 over R bar, right? And here rates are not changing as much. So did that make sense?
Okay.
Yeah, okay. So we are going to use some tools from convex optimization theory to answer this question, to solve this problem. So the primal problem, if we look at just this problem, and I probably will not have enough time to convince you that this is not convex, so we'll take that offline. I'm going to solve the dual problem because the problem is coupled on all tones. And all I'm doing is simplifying the problem. And then I'm going to use a tool called dual decomposition and then solve problem on each tone and come back and solve this problem, basically solve the power constraint aspect. And what we use is a result from optimization theory where when the number of tones are large enough, solving the dual problem is a good enough approximation for solving the primal problem. So here is the overview, and we'll not go through all the details, but this is the dual problem that we are solving. And then this is the tonal subproblem. So the way this formulation works is that I start here, solve the problem on each tone, and then go back here and solve the problem to satisfy the power constraints. So these Lagrange multipliers get configured there. Okay, so let's see how much we want to explain. Yes?
Go back?
Yes.
So what to the previous slide. So what package are you using to use the ellipsoid subgradient method to solve this dual? What's the software package that you use for that?
It's MATLAB. I implemented it by hand.
Oh, okay.
Yeah,
So I was wondering, why don't you sort of the built-in?
Why did I not use the built-in? Because there is an inner loop here, the tonal subproblem too.
There's a what, sorry?
There's an inner loop. You can use the subgradient or ellipsoid if there's only a single problem, right? There's an inner loop.
I see. So this is okay, I see.
So you have to be able to solve the inner problem and then the outer problem, right? If this was the only problem that you were solving, then that was great. So if this problem were directly convex, then that all sounds great. And I'm going to show you can come up with a successive convex approximation, but just to check the convergence properties, I did not use them. You can. I just wanted to make sure that things are converging and everything else. So I've implemented most of the stuff by myself. It's not that hard. So the only two things that I'm going to do in a few minutes is that I'm going to convince you that the non-vectored users, all they were doing was they had these signal to interference noise ratios, right, on which their data rate depended. So your data rate on any chunk or subcarrier depended only on the signal to interference noise ratios. For the vectored users, we are using some interesting sophisticated signal processing, something called as MMSE or minimum mean square decision feedback equalizer. It is implementing successive decoding from information theory, but what is really happening is that if I am the first user to be decoded, I see all the noise, and if I'm the last user to be decoded, I see the least amount of noise because all the other users' crosstalk is no longer seen in my case. And that's how it translates into my formulas that I used for data rates. So there is a notion of who gets decoded first and who gets decoded last. And I'm going to just skip this block because the key intuition is just how things are getting decoded. So the signal to interference noise ratio is based on, it's directly proportional to your own transmit power. But in terms of the powers of other users, it really depends only on the users which are not decoded yet. And for the non-vectored users, it depends on this noise whitening matrix, which shows up in this noise whitening filter. So 2 things to note here. 1, you're only seeing interference from the users which are not decoding yet. And then this noise whitening filter is actually able to correlate the noise from all the non-vectored users and get rid of it. So that makes things very interesting. And so coming back to your original problem, when I take these expressions and want to solve for my power spectra on each tone, I have 2 options. One is either I can go for an exhaustive search of powers because I know the PSD mask limits, or I can go for a successive convex approximation approach. But both of them, by now looking at the problem, are very complex that they cannot be implemented on a 50 to 200 lines binder.
How many levels of power do you have?
How many levels of power? Bits. We are talking about bits. So because this is a discrete bit loading.
You can tune the power to whatever.
You can.
Or is it more very discrete?
Discrete bit loading.
How many are those?
You can load bits between 0 and 15. 15. Because that's how they were going for binary.
And that's how modems or whatever.
Yeah,
right?
On each tone I can load 15 bits. But at most modems will not have loaded 15 on all tones because power constraint would have already been exceeded by then. So, okay. So what I'm showing now is how much you can get out of this theoretical optimum because that's where the interesting space lies. So red curve was already what you were familiar with. In this simulation scenario, 2 users and the third non-vectored line. These were 2 vectored lines. The x-axis was the data rate of vectored users and the y-axis was the data rate of non-vectored users. With the black line, what I'm able to see is that if I choose 100 megabits per second for my vectored users, I'm getting back my 6 megabits per second for the non-vectored line. That's almost 173% gain, or other way to interpret it is that I'm keeping my existing customer at what it was. Alternatively, if I chose to keep it at 6 megabits per second, I'm actually getting the gain of the new technology all the way through. So this is really great because now you can actually get the gains of upgrading these systems. And I'm showing you these 3-line simple examples because I wanted to explain the practical approximation, but we have tested this for 25-line or 50-line simulations also. And why does this work? This is where things actually, we can get to practical approximations. So we're really using the channel structure to our advantage. Here, notice that these are short lines and these are long lines. Long lines means more attenuation. So the colors actually correspond to what are the colors here. We are showing channel magnitude versus frequency all the way up till 30 megahertz. This is short lines channel gain. This is long lines channel gain. So this is more at higher frequencies. This is the interesting part. This is the crosstalk from short user to the long user. Notice that it is greater than the direct channel gain of the long user. So only in this space you can actually get any useful transmission. While for the crosstalk channel from long to short lines, it's way below.
I have to ask the same question again. Is this simulation or is it?
The channels you can, in the real channels it will just be a distribution over what I'm showing. So the crosstalk from short vector lines can dominate the long non-vectored lines. So there is value to actually doing the spectrum optimization just by looking at the channel structure. Now what is happening in mixed irritated water filling, which was the state-of-the-art solution, versus mixed OSP. So this is the power spectra at the point where there was 100 megabits per second on the vectored line. The non-vectored line with the state-of-the-art was getting 2 megabits per second, and the mixed OSP, that's the optimum solution, was getting 6 megabits per second. Notice here, you have 3 bands. The red and blue curves correspond to the 2 vectored lines, and the black curve corresponds to the non-vectored line. When these 2 overlap, you're interfering with each other. When you're interfering with each other, basically the non-vectored line is seeing a lot of power from these vectored lines, and it just backs off and does not load power in these frequencies. On the other hand, in this window, we see that almost gone to orthogonal transmissions, but it's not seeing power from these vectored lines, so it's not seeing as much interference, so it is able to load power. So effectively, you've just exploited the channel structure and figured out which bands to prefer versus which bands to not prefer. So that whole idea of multi-level water filling starts to emerge again. And this is where we are again going to use the concept of multi-level water filling, except that we are going to generalize it to this mixed binder scenarios. And there is a difference because I'm going to water fill on equivalent channel gains for my short vectored lines. So these are not the same channel gains. This 1 over SNR is now just coming out of that whole box that I had for successive decoding. So I start with this water filling distribution on my equivalent channel gains. And then if I'm the short vectored user, I would be given some indication that this band is preferred and this band is not preferred. And there's a way to do that with the existing standard. And then I move bits out of my non-preferred band to my preferred band. And I only stop when I hit the PSD mask. So you basically specify which bands are preferred versus which are not preferred. So this is a variation of what's an existing water filling solution. And the way we indicate whether we are using multi-level water filling versus single-level water filling is using another parameter that exists in the standard called target margin versus max margin. Okay.
By the way, I see a lot of parallels between this work and something that we've been sort of, or this community has been trying to do in white spaces, which is you have the situations of networks which are of different lengths that you're trying to work. So the longer length network gets sabotaged by the shorter length.
Yeah, this is the same near far problem. Yeah,
it sits right next to it. And it's a sort of very serious problem and almost as big a problem that can bring down this whole space if not solved, because you completely lose the advantage of a long-range network if you're always being sabotaged by this short-range network.
That would be very exciting to talk about.
So I don't know how
there would be
this
some
would map there, but I think there's a bunch of
I'm happy to talk more, but I think the questions, time variation at which things happen would be.
Yeah, so the questions in, and let alone what we're asking there, you need to have much finer grain control. Okay. And so
happy to talk further.
Algorithms that kind of map so quickly there, so it's interesting.
Happy to talk further on that. And these cutoff frequencies, they are actually determined using a search algorithm, a bisection search algorithm at the SMC. So let me first go through the gains, and then we'll go through the implementation, why this is simple and practical to implement. So we had seen the black curve earlier, and we had seen the red curve earlier. So the red curve was the state-of-the-art solution, and the black curve was the theoretical optimum for the same scenario, 2 vectored lines, 300 meters, and 1 non-vectored line, 1200 meters. The green and the blue curves now are what we get out of this practical approximation. So the green curve is obtained when we have optimized our cutoff frequencies, or when we have optimized which band to prefer. And the blue curve is when we have chosen just a naive assumption for whatever bands to prefer. In both cases, you see that when I provision my vectored line at 100 megabits per second, you're getting as much as 161% gain with this new algorithm, which is very simple. And at 6 megabits per second, you are basically actually getting some gain out of upgrading to new technology. Now, implementation, because that's what I was pitching earlier. So the Spectrum Management Center has to somehow convey these cutoff frequencies to the modem, and it has to tell them that this is a multi-level water filling solution. The way it conveys the cutoff frequencies is by using the PSD mask and depressing it slightly in different bands. So this is how we got through the standards bodies. But that's the only parameter it's conveying to the modems. Then the modems do their water filling and then change the water filling distribution just like I described. But the fun thing here is that they can adapt. So if they see higher noise in their higher frequencies, then they can water fill back to the lower frequencies instead of coming up with a centralized solution which says, okay, this power spectra, and this is an actual problem in UK networks. They were like, we want to impose this power spectra on anything that's lower than this length. So that's not a robust solution. Okay, so the two important points here are that now you have a very low complexity solution as far as the modems go. You don't have to change anything there. And it's a near distributed. The reason I say near distributed is because you do have to give some information to the modems based on statistics you collect, but not a lot of information. And the modems are able to adapt. Now this slide was basically meant to convey mathematically some of the complexity. So you had mixed iterative water filling, which was suboptimal but very simple. And let me parse the parameters for 1 second. So n is the number of frequency tones. It can go all the way to 4096. K is the number of lines, and K1 is the number of vectored lines. These can be of the order 25 to 50. So the big term here is n log n in terms of the number of frequencies. So mixed iterative water filling was very simple. Mixed OSB, which is theoretically optimum, is exponential in the number of users and then linear in the number of tones. Where we get most of the gains are by changing this term to this. But I already explained the intuition of why this is really simple to implement. And we basically got it through standards. So this was a summary slide of what the work that I have done in proposing these energy or how do you control the power levels in next generation DSLs. And I basically led the standardization of this to the Kostney report, which got published last year. I was actually, the kind of data rate gains we have gotten are in the range of 50 to 160%. Okay. So this was a research summary so far of what we have done in the space of DSLs and next generation DSLs. We are exploring some of these ideas also extend to coaxial cable networks, and I was hoping to spend 5 minutes on that, and that would be the end of my talk. Is that good? Okay. Or if people want me to stop here, I'll just give a research summary and we can do this in question and answer session too. Your call. Okay. So coaxial cables, that's the other medium that we talked about for wireline access. This is really a waveguide. So historically, this was deployed because TV networks were deployed, and it is heavily deployed in North America, but if you look at everywhere else, the penetration of DSLs is higher. But what's interesting is that you're basically going to send signal between the center conductor and the outer shield, so this is really a waveguide, or so to say. Where cable networks are going now is that they have these head-end distributions, and then these drop cables going all the way up to each home. So you have the signal starting here and then going all the way here. So this is your cable network, and it will be shared between multiple homes. So if you have a cable provider telling you that I provide gigabits per second speeds, it will be shared with all your neighbors. And how many neighbors it can be shared with? It can be all the way up till 500 to 2,000. So what's interesting in this space is that they are increasingly moving towards something called as hybrid fiber coaxial system, because they want to bring down this 500 to 2,000 to 50 to 200. Just like DSLs, they're basically trying to move fiber closer to you so that the coaxial cable is smaller length and the rates are higher, so they can get higher data rates for smaller number of users. And currently, it's lying in the range of 38 megabits per second downstream and 27 megabits per second upstream. This was DOCSIS 1.x. But they're going all the way to 10 to 2 gigabits per second with DOCSIS 3.1, which is something that you might have read in news because that's an up-and-coming standard for cable networks. Now, what is interesting here is that they're moving in two directions. One, they are going for multi-carrier systems with better coding, and they're expanding the spectrum that they can operate in. So as TVs vacated that analog space, not only white spaces became hot, but cable networks are also doing work to use this for data. So existing plans, for example, they had this 42 megahertz that they were using. Now they're trying to decide between mid-split, high-split, and top-split, which basically are different configurations of spectrum. But what is interesting is that they right now are operating in the space of 100 megabits to 300 megabits per second, and they basically want to get here. So which one they decide depends on certain logistics of what amplifiers to replace and what to do. Where we are active here is that basically this is a shared system in time dimension. What we are exploring is whether you can get more out of doing multi-user techniques. Can you superimpose signals and do better? And that gets really interesting because now you can share things between multiple users. And given that now it's becoming a multi-carrier system, you can do this on different bands. And they have fairly flat bands with attenuation changes for different bands, but it's not a lot of variation in adjacent frequencies. So the key point to take away here is that's an interesting space which is moving towards gigabits per second, but more is probably possible by using certain interesting techniques, and we are looking at how we can use this shared medium better by using other dimensions. So this is an ongoing project, and I cannot say more. So this was my work in coaxial cable networks, and then I have also done some work in multi-cell wireless networks on similar ideas of limited, basically using these mixtures of interference and multiple access channel, and I can talk more about it. Then I had one project in home power line communications for those who are interested, where I was using the cyclostationarity in power lines to propose an opportunistic CSMA protocol. And that was a fun project to learn all about power lines and CSMA at the same time. And this was the work I did at Microsoft Research with Technology Policy Group. And this was basically to investigate how much opportunity is there for unlicensed secondary usage in 30 megahertz to 6 gigahertz spectrum using the data from Microsoft Spectrum Observatory at Technology Policy Group. And this, Ranvi tells me, has gone into an NPR to reply for an NPRM. So that's that impact. And that's the summary of the various research projects that I've looked at. That would be the end of my talk.
Question. I mean, you've done a lot of work on this vector DSL basically modems.
Yes.
I assume you also basically track the work on wireless interference management.
Yes. So I have papers on multi-cell wireless.
How do you compare these two specs, wireless interference versus DSLs, basically crosstalk? What's similar? What's different?
Can you kind of elaborate your question? I mean, are you trying to get an idea of what the literature looks like, or what's?
No, basically first, like basically the two channels.
Okay.
What are the similarity and difference between these two spaces? The channel characteristics, I mean stability, I mean estimation of, for example, the crosstalk matrix.
Okay.
I mean.
No, I think, so you're asking a very interesting question, and I think as you probably know, whenever you're comparing wireless versus wireline, wireline tends to be more stationary channel compared to wireless, where things are changing at much faster rate. As a result, whatever channel estimation you are doing here, things are not accurate. I'm not going to say they're accurate, but here, by the time you get any information, you're not going to be able to use it, right?
Did you measure, or did you see measurement work on the
wireless side?
Yes.
No.
A wireless side and the.
I've seen measurements on DSLs, not on wireless.
Okay.
Not on wireless aspects. I've only seen channel models on wireless.
The reason basically I ask this is, I mean, basically in terms of practical implementations, right?
Yeah.
The channel characteristics.
So the practical implementations for multi-cell work are happening at Alcatel-Lucent. I talked to those folks, but I haven't seen the measurements myself.
So we have measurements, so it would be nice to validate the wireless experimentation.
Okay. Yeah, I'm not an expert in that area. I just was taking all my work and seeing if it applies and what kind of gains are possible in simulations.
For this, basically, for the last work you talk about, basically energy, basically allocation. Is it possible, basically, to basically project a zero vector onto those unlicensed?
I was thinking about that. So you're thinking in terms of interference alignment. One of the key requirements of interference alignment is that the number of dimensions has to be larger, right? Yeah. In this case, we are transmitting on all the dimensions that we are actually using. So we have 3 dimensions, we're using all 3. If I had one extra wire, which is possible, because if you, so this is differential, so you have a twisted pair, so you are using the difference of the 2 signals on the 2 lines. If you basically make it common vectoring, then what you use the binder as the reference point and use all the other wires from there. Then you have this additional antenna, and then you can start talking about the kind of things you're talking. But here, if you use all the transmit dimensions, then you're not going to be able to do it. And then you have to meet all those constraints of the papers that came out as to whether I can actually use those transmit dimensions or not.
What do you mean the Marconi word for?
We work on vectored and non-vectored DSLs because it was taken all the way to standards. So it was really end-to-end work in terms of impact. Thank you.